Something massive is hiding at the edge of our solar system. And it is not what you think. For decades, scientists believed they understood the outer reaches of our cosmic neighborhood. They mapped the planets. They charted the moons. They tracked the comets and asteroids. But beyond the orbit of Neptune, in a frozen twilight zone called the Kuiper Belt, the numbers simply do not add up. Objects are moving in ways they should not. Orbits are tilting at angles that make no sense. And strangest of all, the belt itself seems to end, abruptly, as if someone or something drew a line in the darkness and said no further. If you enjoy exploring the mysteries of the cosmos with us here at Cosmic Drift, please take a moment to hit the like button and subscribe. It helps us bring you more journeys like this one into the unknown. Now, when most people hear about a hidden massive object in the outer solar system, they think of Planet 9. That hypothetical giant world has captured headlines for nearly a decade. But tonight, we are going to explore something different, something potentially stranger. Because while the whole world searches for a missing planet, a quieter idea has been growing among astronomers. An idea that what lurks in the Kuiper Belt might not be a planet at all. It might be a black hole, or a concentrated ring of dark matter, or the gravitational ghost of a world that was thrown out of our solar system billions of years ago. To understand why scientists are even considering such possibilities, we need to start at the beginning. We need to understand what the Kuiper Belt actually is, why it matters, and what has gone so terribly wrong with our models of the outer solar system. So settle in, get comfortable, let your eyes grow heavy if they want to, because this is going to be a long, slow journey to the very edge of everything we know. The story of the Kuiper Belt begins with a question that haunted astronomers for over a century. Where do comets come from? These icy wanderers have fascinated humanity since the dawn of recorded history. They streak across our skies, their tails blazing behind them, before vanishing back into the darkness from which they came. But comets have a problem. They cannot last forever. Every time a comet swings close to the sun, its surface heats up. The ice sublimates, turning directly from solid to gas. Material streams away, forming that beautiful glowing tail we admire from Earth. But that process also destroys the comet, bit by bit. A typical comet might survive a few hundred passes by the sun before it breaks apart completely or loses all its volatile material. So if comets are constantly being destroyed, and yet we keep seeing new ones, there must be a source. Somewhere out there in the cold and the dark, there must be a reservoir of icy bodies waiting to be nudged toward the inner solar system. In the 1950s, a Dutch astronomer named Jan Oort proposed that a vast spherical cloud of icy objects surrounds the solar system at enormous distances. This Oort cloud, as it came to be known, could contain trillions of frozen bodies, occasionally disturbed by passing stars and sent tumbling toward the sun. That explained the long-period comets, the ones that take thousands or even millions of years to complete a single orbit. But what about the short-period comets, the ones that zip around the sun every few decades? They seem to come from a different direction entirely. They orbited close to the plane of the solar system, not from random angles like the long-period visitors from the Oort cloud. Around the same time that Oort was developing his theory, another astronomer was thinking about this problem. Gerard Kuiper, working at the University of Chicago, suggested that a belt of icy bodies might exist just beyond the orbit of Neptune. These objects would be the leftover building blocks from the formation of the solar system, frozen relics from a time when the sun was young and the planets were still taking shape. Kuiper imagined this belt as a relatively modest collection of debris. He actually thought that most of it had been swept away or scattered outward by the gravitational influence of the planets. In a strange twist of irony, Kuiper essentially predicted that the belt named after him should not exist anymore, but Kenneth Edgeworth, a British astronomer, had proposed something similar a few years earlier. He suggested that the region beyond Neptune was occupied by a very large number of comparatively small bodies. These objects, he theorized, occasionally wandered from their distant orbits and appeared as occasional visitors to the inner solar system. For decades, these ideas remained purely theoretical. The technology simply did not exist to detect such small, faint, distant objects. Telescopes of the mid-20th century could barely make out the dim glow of Pluto, discovered in 1930 and sitting at an average distance of about 40 astronomical units from the Sun. 1 astronomical unit, or AU, is the distance from Earth to the Sun, roughly 93 million miles. Finding anything smaller than Pluto at those distances seemed impossible, but astronomers kept looking and waiting and improving their instruments. The breakthrough came in 1992, when David Jewett and Jane Liu, using the University of Hawaii telescope, discovered a tiny, faint object orbiting far beyond Neptune. They designated it 1992 QB1, and it was the first confirmed Kuiper Belt object other than Pluto. The belt that Kuiper and Edgeworth had imagined was real. Over the next 3 decades, the discoveries multiplied. Today, astronomers have catalogued over 1,000 objects in the Kuiper Belt, with estimates suggesting there could be hundreds of thousands more waiting to be found. Some of these objects are substantial, like the dwarf planets Eris, Makemake, and Haumea. Others are small, just a few miles across, tumbling silently through the eternal twilight. The Kuiper Belt stretches from the orbit of Neptune at about 30 astronomical units to roughly 50 astronomical units from the Sun. That is a vast region of space, far larger than the asteroid belt between Mars and Jupiter. And unlike the rocky asteroids of the inner solar system, Kuiper Belt objects are composed primarily of frozen volatiles: water ice, methane ice, ammonia ice. They are cosmic snowballs, unchanged since the earliest days of our solar system 4.5 billion years ago. Studying these ancient relics tells us about the conditions that existed when the planets were forming. They are, like time capsules, preserving the chemistry and composition of the primordial solar nebula. When scientists examine a Kuiper Belt object, they are looking at material that predates the Earth itself. But as astronomers mapped more and more of the Kuiper Belt, they started noticing something strange. The distribution of objects was not what they expected. The models that explained how the solar system formed predicted a gradual decline in the number of objects as you moved outward from Neptune. Instead, they found something much more abrupt. Around 50 astronomical units from the Sun, the Kuiper Belt seems to end. Not gradually, not gently, but sharply. The number of objects drops off dramatically, as if someone sliced through the belt with a cosmic knife. This feature has come to be known as the Kuiper Cliff, and no one knows what caused it. The Kuiper Cliff is one of the most puzzling features of our solar system. According to our best models of planetary formation, there should be more objects beyond 50 astronomical units, not fewer. The primordial disk of gas and dust that formed the planets extended far past that boundary. There was plenty of material out there to form Kuiper Belt objects. So where did it all go? One possibility is that we simply have not looked hard enough. Objects at those distances are incredibly faint. They reflect very little sunlight, and what light they do reflect has to travel enormous distances to reach our telescopes. Perhaps the belt does continue beyond 50 AU, but the objects out there are just too small or too dark for us to see. This was a reasonable hypothesis for a while, but as telescope technology improved and surveys grew more comprehensive, the cliff remained. In 2003, astronomers conducted careful observations that confirmed the rapid decline was real. It was not just an artifact of observational bias. There genuinely are far fewer large objects beyond 50 astronomical units than our models predict. Another possibility is that something swept the outer belt clean. Perhaps a massive planet formed in that region long ago, gobbling up all the smaller bodies or flinging them out into the distant Oort cloud. This planet, if it existed, might have eventually been ejected from the solar system entirely, leaving behind only the evidence of its passage in the form of the Kuiper Cliff. Or perhaps the primordial disk of material simply ended at about 50 AU. Maybe the solar nebula was smaller than we thought, and there was never enough material out there to form objects in the first place. This would require revising our understanding of how the solar system formed, but it remains a possibility. The truth is, we do not know. The Kuiper Cliff remains an unsolved mystery, one of those nagging questions that keeps astronomers awake at night. And it was just the first hint that something strange was going on in the outer solar system. Because around the same time that scientists were puzzling over the cliff, they started discovering objects with orbits that made even less sense. In 2003, a team led by Mike Brown at Caltech discovered a reddish, distant object that they initially nicknamed the Flying Dutchman. Its official designation was 2003 VB12, but it eventually received the name Sedna, after the Inuit goddess of the sea. Sedna was different from anything astronomers had seen before. Its orbit was enormous, taking over 11,000 years to complete a single trip around the Sun. At its closest approach, it came within about 76 astronomical units of the Sun. At its farthest, it swung out to nearly 1,000 astronomical units. But the truly strange thing about Sedna was its perihelion, the point where it comes closest to the Sun. At 76 AU, Sedna never gets anywhere near Neptune. The giant planet orbits at only 30 AU. That means Neptune's gravity cannot possibly be responsible for Sedna's elongated orbit. Something else had to put it there. This was deeply puzzling. In our current understanding of the solar system, the gravitational influence of the giant planets shapes the orbits of smaller objects. Neptune, in particular, has swept through the outer solar system, scattering some objects outward, trapping others in orbital resonances, and generally organizing the Kuiper Belt into its current structure. But Sedna exists beyond Neptune's reach. It is detached from the rest of the solar system, following its own lonely path through the darkness. How did it get there? One idea is that a passing star disturbed Sedna's orbit billions of years ago, when the Sun was still part of its birth cluster. Stars form in groups, and the early solar system would have had many close neighbors. A near miss from another star could have tugged on objects in the outer solar system, pulling some into highly elongated orbits like Sedna's. Another possibility is that Sedna was captured from another star entirely. Perhaps it originally formed around a different sun and was stolen during a close encounter between stars in the early days of the galaxy. This would make Sedna an immigrant, a foreign body that became trapped by our sun's gravity. Or perhaps there is something massive out there that we have not discovered yet, something whose gravitational influence reached out and lifted Sedna into its unusual orbit, something hiding in the darkness. For years after Sedna's discovery, astronomers searched for similar objects. If Sedna was the result of some systematic process, whether a passing star or an undiscovered planet, there should be more like it. In 2014, Chad Trujillo and Scott Shepard announced the discovery of 2012 VP-113, another object with a similarly detached orbit. Its perihelion was even farther out than Sedna's, at about 80 astronomical units. And then they noticed something peculiar. When they looked at the orbital parameters of these extreme objects, they seemed to cluster together. The arguments of perihelion, a technical term describing the orientation of an orbit, were all close to the same value. It was as if something was herding these distant objects, keeping them aligned like cattle in a celestial corral. The probability of this clustering happening by random chance was less than 1 in 100. Something was going on. Trujillo and Shepard suggested that a massive distant planet could be responsible. Its gravity would shepherd the extreme trans-Neptunian objects into similar orbits, maintaining their alignment over billions of years. This idea caught the attention of other astronomers, including Mike Brown, the discoverer of Sedna. In 2016, Brown and his colleague Konstantin Batygin at Caltech published a landmark paper. They had analyzed the orbits of 6 extreme trans-Neptunian objects and found strong statistical evidence for clustering, not just in the argument of perihelion, but in other orbital parameters as well. The objects were not only pointing in similar directions, they were also tilted off the plane of the solar system by about the same amount. Batygin and Brown ran computer simulations to determine what kind of object could produce such clustering. Their conclusion was striking. A planet with a mass of about 10 times that of Earth, orbiting at an average distance of around 600 astronomical units, could explain all the observed features. They called it Planet 9. The announcement made headlines around the world. A new planet in our own solar system, hiding in the darkness just beyond our view. It was the most exciting astronomical claim in decades. But there was a problem. Despite years of searching, no one has found Planet 9. Astronomers have scanned vast swaths of the sky with some of the most powerful telescopes on Earth. They have used sophisticated software to search for slowly moving points of light against the background stars. They have recruited citizen scientists to help examine millions of images. Nothing. This absence of evidence has led some researchers to question whether Planet 9 exists at all. Perhaps the clustering is just a statistical fluke, the result of small sample sizes and observational biases. Perhaps we are seeing patterns that are not really there, but the evidence keeps accumulating. More extreme trans-Neptunian objects have been discovered, and many of them continue to show the clustering that Batygin and Brown predicted. In 2024, the team published new research analyzing 17 such objects and found what they called the strongest statistical evidence yet for Planet 9. They estimated the probability of the clustering being random at about 1 in a million. If Planet 9 is real, it has managed to hide from our searches for nearly a decade. That is remarkable for an object so massive, but it is also not impossible. The outer solar system is vast beyond comprehension. A dim, distant planet on a highly elongated orbit could easily evade detection, especially if it is currently near aphelion, the farthest point in its orbit. The Vera Rubin Observatory in Chile, scheduled to begin full operations in 2025, may finally settle the question. This next-generation telescope will survey the entire visible sky every few nights, capturing images of remarkable depth and clarity. If Planet 9 exists and is anywhere within its predicted range, Rubin should be able to find it within a year or two. But here is where our story takes a twist. Because while everyone has been focused on finding a missing planet, some astronomers have been asking a different question entirely. What if Planet 9 is not a planet at all? What if it is something much stranger? The idea that something other than a planet might be lurking in the outer solar system sounds like science fiction. But in 2019, two physicists published a paper that made astronomers take the possibility seriously. Jakob Scholz from Durham University and James Unwin from the University of Illinois at Chicago asked a simple question. What if the gravitational effects we attribute to Planet 9 are actually caused by a primordial black hole? Primordial black holes are theoretical objects that differ fundamentally from the black holes we usually talk about. Most black holes form when massive stars collapse at the end of their lives. These stellar black holes have masses ranging from a few times that of our Sun to tens of solar masses. The supermassive black holes at the centers of galaxies are even larger, containing millions or billions of solar masses. But primordial black holes would have formed in a completely different way. In the first fractions of a second after the Big Bang, the universe was an incredibly dense, hot soup of matter and energy. In some regions, the density was slightly higher than average. If these overdense regions were dense enough, they could have collapsed directly into black holes without ever forming stars first. The key difference is that primordial black holes could be much, much smaller than stellar black holes. While a stellar black hole requires at least a few solar masses to form, a primordial black hole could theoretically have any mass at all. Some might be as massive as mountains, others might be as light as asteroids, and some, intriguingly, might have masses similar to what we expect for Planet 9. Scholz and Unwin pointed out that a primordial black hole with a mass of about 5 to 10 times that of Earth would produce exactly the same gravitational effects as a planet of the same mass. The distant objects in the Kuiper Belt can't tell the difference. They only feel the gravitational pull. They do not care whether that pull comes from a ball of rock and ice, or from a region of space-time so warped that not even light can escape. If this sounds far-fetched, consider the evidence. Or rather, consider the lack of evidence. Despite years of searching, no one has directly observed Planet 9. We have not detected the infrared radiation that a large cold planet should emit. We have not seen the faint reflected light from such an object. All we have is the gravitational signature, the clustering of orbits, the unexplained perturbations. A primordial black hole would explain this perfectly. Such an object would emit no light at all. It would be completely invisible to our optical and infrared telescopes. The only way to detect it would be through its gravitational effects, which is precisely what we observe. But wait, you might be thinking, would not a black hole in our solar system be dangerous? Would not it be sucking in matter and growing larger over time? This is where the scale becomes important. A primordial black hole with 5 Earth masses would have an event horizon, the boundary from which nothing can escape, of only about 5 centimeters. That is roughly the size of a tennis ball. Think about that for a moment. All that mass compressed into a sphere smaller than a baseball. The gravitational effects at astronomical distances would be identical to those of a planet, but the actual object would be vanishingly small. It would not actively suck in matter, because matter would have to get incredibly close to fall past the event horizon. At the distances we are talking about, hundreds of astronomical units from the Sun, there is essentially nothing nearby to consume. Such a tiny black hole would drift silently through the outer solar system, invisible and harmless, its presence known only through the gentle gravitational tugs it exerts on distant icy bodies. Schultz and Unwin also pointed to another intriguing piece of evidence. Around the same time they published their paper, a survey called OGLE had detected an unusual number of microlensing events toward the center of our galaxy. Microlensing occurs when a massive object passes in front of a distant star. The object's gravity bends the light from the star, causing it to brighten temporarily. By studying these brightening events, astronomers can learn about the masses of the objects causing them. The OGLE survey found more events than expected for objects with masses around 5 to 10 times that of Earth. One explanation was a population of free-floating planets drifting through the galaxy. But another explanation was a population of primordial black holes. If primordial black holes of this mass exist in significant numbers, it becomes more plausible that our solar system might have captured one during its early history. The Sun formed in a cluster of other stars, and the early solar system was a chaotic place. A passing black hole could have been gravitationally captured, settling into a distant, stable orbit around the Sun. The probability of capturing such an object, Schultz and Unwin argued, was comparable to the probability of capturing a rogue planet. Both scenarios involve capturing a free-floating object from interstellar space. Since astronomers already consider planet capture a reasonable explanation for Planet 9's origin, black hole capture should be taken equally seriously. This idea generated significant interest in the astronomical community. Konstantin Batygin, one of the original proponents of the Planet 9 hypothesis, acknowledged that a primordial black hole could explain the gravitational evidence just as well as a planet. As he put it, all we know is that there is a several Earth mass something out there. We do not know what that something is, but how could we ever tell the difference? How could we distinguish between a cold, distant planet and a tiny, invisible black hole? In 2020, astronomers at Harvard proposed a method. Avi Loeb and his student Amir Siraj suggested that a black hole in the outer solar system would occasionally encounter small bodies from the distant Oort cloud. When a comet or icy object gets too close to a black hole, it would be torn apart by tidal forces. The material would spiral inward, heating up and producing a brief flare of radiation before disappearing past the event horizon. These flares would be faint, but they might be detectable with the right instruments. Loeb and Siraj calculated that the upcoming Vera Rubin Observatory should be able to spot such flares if a black hole exists in the outer solar system. The telescope's wide field of view and high sensitivity make it ideal for detecting transient events anywhere in the sky. If Rubin detects flares from a specific location in the outer solar system, it would be strong evidence for a black hole rather than a planet. And even if it does not detect any flares, the absence of observations could place constraints on the fraction of dark matter that might be composed of primordial black holes. The black hole hypothesis is just one alternative to Planet 9. Other researchers have proposed different explanations for the clustering of extreme trans-Neptunian objects. One idea involves the galactic tide. Our solar system is not isolated in space. It orbits around the center of the Milky Way galaxy, and it feels the gravitational pull of the rest of the galaxy's mass. This pull is subtle, but over billions of years, it can affect the orbits of objects in the outer solar system. Some astronomers have suggested that the galactic tide, combined with the scattering effects of Neptune, might be able to produce the observed clustering without any additional massive object. The gravitational influence of the galaxy as a whole could shepherd distant objects into similar orbits. However, studies that have looked at this possibility in detail have generally found that the galactic tide alone cannot reproduce all the features of the observed clustering. It might contribute to the effect, but it does not seem sufficient as a complete explanation. Another alternative involves a massive disk of material in the outer solar system. Rather than a single large planet, perhaps the gravitational effects are caused by the collective pull of many smaller objects spread over a wide region. If there is significantly more mass in the Kuiper Belt than we currently estimate, it could potentially affect the orbits of the extreme trans-Neptunian objects. This idea is intriguing because it connects to another puzzle, the Kuiper Cliff. If the belt originally contained much more mass that was somehow depleted or hidden, that same mass could now be spread out at greater distances, forming a diffuse gravitational structure. However, for this to work, the mass would need to be concentrated in a way that produces the specific clustering pattern we observe. A uniform disk of material would not create the clustering. The mass would need to be distributed in a particular way, which raises questions about how such a distribution could arise. A more exotic possibility involves modifications to our understanding of gravity itself. In 2023, researchers showed that a theory called modified Newtonian dynamics, or MOND, could potentially explain the clustering of distant objects without requiring any hidden mass at all. MOND was originally proposed to explain the rotation curves of galaxies without invoking dark matter. The theory suggests that gravity behaves differently at very low accelerations than Newton's laws predict. In the outer reaches of a galaxy, where gravitational accelerations are extremely weak, MOND predicts stronger gravitational effects than Newtonian physics would. The outer solar system, far from the Sun's strong gravitational influence, is exactly the kind of environment where MOND effects might become relevant. If gravity works differently at these distances, it could naturally produce clustering without any hidden planet or black hole. But MOND remains controversial. While it has some success in explaining galactic rotation curves, it struggles with other observations, particularly in galaxy clusters. Most astronomers still favor the existence of dark matter over modifications to gravity, and MOND would need to be extended in specific ways to explain the solar system observations, which introduces additional complications. The truth is, we do not yet know what is causing the strange behavior we observe in the outer solar system. It could be a planet, it could be a black hole, it could be something else entirely that we have not thought of yet. What we do know is that the evidence for some kind of massive object continues to grow. The clustering is real. The unexplained orbits exist. Something is out there, shaping the architecture of the outer solar system. And that brings us to the most recent discoveries, the ones that have made this mystery even deeper and more fascinating. In early 2024, NASA's New Horizons spacecraft, still cruising through the Kuiper Belt, after its historic flybys of Pluto and Arakoth, detected something unexpected. Its onboard dust counter was measuring higher than expected levels of dust particles far beyond where the Kuiper Belt was supposed to end. This was puzzling. Dust in the Kuiper Belt comes primarily from collisions between larger objects. When two icy bodies crash into each other, they break apart and produce a cloud of smaller particles. The amount of dust should correlate with the number of objects in a region. So, if there was more dust, there should be more objects producing it. Alan Stern, the principal investigator for New Horizons, announced that the spacecraft had found evidence for a second Kuiper Belt, or perhaps an extension of the existing belt far beyond the 50 AU boundary that had long been considered its outer edge. The discovery aligned with observations from ground-based telescopes. Using the Subaru telescope in Hawaii, astronomers had been searching for Kuiper Belt objects as potential targets for new horizons. In the process, they discovered 11 objects at distances well beyond the traditional Kuiper Belt, stretching out to 70, 80, even 90 astronomical units from the Sun. These discoveries suggest that our picture of the Kuiper Belt has been incomplete. The belt might not end at the Kuiper Cliff after all. Instead, it might extend much farther, perhaps blending gradually into the inner reaches of the Oort cloud. This has profound implications for our understanding of the solar system's structure. If the outer belt contains significantly more mass than we previously realized, it could help explain some of the gravitational anomalies we observe. It might also provide clues about the early history of the solar system and the processes that shaped its current configuration. But the discoveries also raise new questions. If objects exist at these great distances, how did they get there? Were they scattered outward by Neptune's gravitational influence? Were they captured from interstellar space? Or did they form in place from a primordial disk that extended farther than we thought? And critically, could these distant objects tell us anything about what else might be lurking out there? In 2018, astronomers announced the discovery of another extreme object that added a new piece to the puzzle, known as 2015 TG387, later named Leleakuhonua after the Hawaiian creation goddess. This object has one of the most distant orbits ever recorded for a solar system body. Leleakuhonua's perihelion, its closest approach to the Sun, is about 65 astronomical units. Its aphelion, its farthest point, reaches beyond 2,000 astronomical units. It takes approximately 40,000 years to complete a single orbit. Like Sedna and 2012 VP113 before it, Leleakuhonua is a sednoid, a member of a rare class of objects with extremely high perihelia that place them beyond Neptune's gravitational influence. And like those earlier discoveries, its longitude of perihelion appeared to cluster with the others, strengthening the case for some unseen shepherd. But then, in 2023, astronomers discovered a fourth sednoid that threw a wrench into the works. The object, designated 2023 KQ14 and nicknamed Ammonite, has orbital characteristics similar to the other sednoids. Its perihelion is about 66 astronomical units, and its semi-major axis exceeds 200 AU. But unlike Sedna 2012 VP113 and Leleakuhonua, Ammonite's orbit is oriented differently. The longitude of perihelion for Ammonite is roughly opposite to those of the other three sednoids. If Planet 9 were shepherding these objects into aligned orbits, Ammonite should be grouped with the others. Instead, it seems to contradict the pattern. This discovery has complicated the Planet 9 hypothesis. Simulations show that if Planet 9 exists with the orbital parameters originally proposed, it would likely eject an object on an orbit like Ammonite's. The fact that Ammonite exists and has remained stable for billions of years suggests that something is different. One possibility is that Planet 9's orbit is more distant or differently oriented than initially thought. If the planet is farther away, its gravitational influence would be weaker, potentially allowing more orbital diversity among the extreme trans-Neptunian objects. Another possibility is that Planet 9 once existed, but has since been ejected from the solar system. This rogue planet hypothesis suggests that a massive world disturbed the orbits of the sednoids during the early history of the solar system then was itself flung into interstellar space by a gravitational encounter with another planet. If this happened, the current clustering of most sednoids would be a fossil imprint of that ancient event. The primordial alignment would have been stronger immediately after the ejection, then gradually randomized over billions of years. Ammonite's different orbit might simply reflect this ongoing randomization process. A 2023 study by astronomers at the National Astronomical Observatory of Japan examined this possibility. They traced the orbits of the known sednoids backward in time, through billions of years of gravitational evolution. Surprisingly, they found that all the sednoids were more tightly clustered 4.5 billion years ago than they are today. This primordial alignment was most pronounced at a specific orientation, suggesting that whatever event created it occurred at a particular moment in the solar system's history. The most natural explanation is a rogue planet that interacted with these objects during the era of planet formation, then departed. This interpretation is exciting because it connects to broader theories about the solar system's early evolution. The NACE model, named after the French city where it was developed, proposes that the giant planets underwent a period of dramatic reorganization during the first few 100 million years after the solar system formed. According to this model, Jupiter, Saturn, Uranus, and Neptune originally formed closer together and closer to the Sun than they are today. Interactions with a massive disk of planetesimals caused their orbits to shift. Neptune migrated outward dramatically, perhaps from 15 or 20 AU to its current position at 30 AU. This migration swept through the Kuiper Belt, sculpting its structure and scattering many objects outward. Some versions of the NICE model even include a fifth giant planet that was eventually ejected. This hypothetical ice giant would have had a mass similar to Neptune or perhaps smaller, a few times that of Earth. Its ejection would have been one of the violent events that reshaped the outer solar system. Could this fifth planet be responsible for the sednoid orbits? Could its ancient influence still be visible today in the clustering of extreme trans-Neptunian objects? The evidence is circumstantial but intriguing. The timing of the primordial alignment matches the era when such an ejection would have occurred. The gravitational signature is consistent with a planet mass object interacting with the outer solar system and then departing. If true, this would mean that the mysterious mass influencing the outer solar system is not there anymore. It has been gone for billions of years, wandering through the galaxy as a rogue planet, leaving behind only its gravitational ghost. But this interpretation does not explain everything. The ongoing stability of the sednoid clustering is harder to maintain without a present-day perturber, and it does not account for some of the other anomalies we observe, like the Kuiper Cliff or the unexpectedly high dust levels detected by New Horizons. Perhaps both explanations contain elements of truth. Perhaps a rogue planet created the primordial alignment, and something else, a surviving planet, a black hole, an extended belt, maintains it today. The outer solar system, it seems, has many secrets yet to reveal. To truly appreciate what is happening at the edge of our solar system, we need to understand how remarkable it is that we can detect anything there at all. The distances involved are almost impossible to comprehend. Light itself, the fastest thing in the universe, takes over 4 hours to travel from the Sun to Neptune. To reach Sedna at its current distance, light needs about 13 hours. At Sedna's farthest point, it would take nearly 6 days. Now imagine trying to see a dim, frozen object at those distances. The sun's light has to travel all the way out there, bounce off the object's icy surface and travel all the way back to our telescopes on Earth. By the time it reaches us, that light has become impossibly faint. Consider this comparison. The full moon appears bright in our night sky because it is relatively close, only about 1 light second away, and it reflects a significant amount of sunlight. A Kuiper Belt object at 50 AU receives only about 1/400th as much sunlight as the moon, because sunlight spreads out as it travels. And that object is far smaller than the moon, so it has less surface area to reflect what little light reaches it. The result is that even the largest Kuiper Belt objects appear as tiny, dim specks in our best telescopes. Pluto, the most famous resident of the belt, has an apparent magnitude of about 14. That means it is about 4,000 times fainter than the dimmest star visible to the naked eye. Smaller objects are fainter still, and more distant objects almost invisible. Detecting these objects requires patience, precision, and powerful technology. Astronomers take long exposure images of small patches of sky, then compare images taken hours or nights apart. If a faint dot has moved relative to the background stars, it might be a new solar system object. Then they track it over weeks or months, carefully measuring its position to calculate its orbit. This painstaking work has revealed the structure of the outer solar system piece by piece. Each new discovery adds another data point to our models, another constraint on what might be out there. And slowly, patterns have emerged. The Kuiper Belt is not a uniform ring of debris. It has structure and texture, regions where objects cluster and gaps where few are found. Much of this structure can be traced to Neptune's gravitational influence. Neptune's gravity creates resonances, special orbital patterns where objects complete a specific number of orbits for every orbit Neptune makes. The most famous resonance is the 2-3 resonance, where objects orbit the Sun twice for every 3 Neptune orbits. Pluto occupies this resonance, along with hundreds of other objects called plutinos. These resonances act like gravitational safe zones. Objects trapped in them have stable orbits that prevent close encounters with Neptune. Without the protection of a resonance, objects that cross Neptune's orbit eventually get scattered, either thrown outward into the scattered disk or flung into the inner solar system, where they become short-period comets. The classical Kuiper Belt lies between the main resonances, extending from about 40 AU to the edge at roughly 48 AU. Objects here, called cubewanos after the first discovered member 1992, QB1, have relatively circular stable orbits. They are thought to have formed more or less where they are today, undisturbed by Neptune's migration. But the classical belt itself has structure. Astronomers distinguish between hot and cold populations based on the inclinations of their orbits. The cold population has low inclinations, meaning their orbits stay close to the plane of the solar system. The hot population has higher inclinations, with orbits tilted 10, 20, even 40 degrees above or below the plane. These two populations have different properties. The cold population tends to be redder in color, suggesting surfaces rich in organic compounds called tholins. The hot population is more diverse, with colors ranging from red to neutral gray. The existence of two distinct populations within the same region of space hints at different origins or different evolutionary histories. Beyond the classical belt lies the scattered disk. Objects here have been disturbed by Neptune at some point in their history, flung onto elongated inclined orbits that carry them far from the Sun. Some scattered disk objects have perihelia that still bring them close to Neptune. allowing ongoing gravitational interactions. Others have been detached, their perihelia lifted high enough that Neptune can no longer reach them. The sednoids represent the most extreme examples of detached objects. Their perihelia are so distant that nothing in the known solar system can explain their orbits. They are fossils from some ancient event, preserved in the frozen darkness for billions of years. And then there is the gap, beyond about 50 AU, where the 1 to 2 resonance with Neptune lies. The population of objects drops sharply. This is the Kuiper cliff, and it remains unexplained. What would fill this gap? What could sweep away the objects that should exist there? A massive planet is one answer. If a large world orbited in this region, it would gravitationally clear its path, either absorbing smaller objects or flinging them elsewhere. This is actually one of the criteria that defines a planet under the current astronomical definition. A planet dominates its orbital zone. But Planet 9, as currently hypothesized, orbits much farther out, hundreds of astronomical units from the Sun. Its influence would be felt differently than a planet orbiting at 50 or 60 AU. It could shepherd distant objects into aligned orbits, but it would not necessarily create the sharp inner edge that we observe as the Kuiper cliff. This suggests that either Planet 9's orbit has different properties than currently estimated, or there are multiple phenomena at work. Perhaps the Kuiper cliff was created by one process, and the clustering of extreme trans-Neptunian objects by another. One intriguing possibility connects back to the early history of the solar system and the NICE model of planetary migration. According to the NICE model, Neptune originally formed closer to the Sun, perhaps around 15 to 20 AU. Over tens of millions of years, interactions with a massive disk of planetesimals caused Neptune to migrate outward. As it moved, it swept through the Primordial Kuiper Belt, scattering objects and shaping the belt structure. This migration explains many features of the current belt, including the resonant populations and the existence of the scattered disk. But it also predicts that Neptune should have stopped migrating when it reached the edge of the planetesimal disk. If the disk extended to about 30 AU, Neptune would have settled at about 30 AU, which is where we find it today. But what if the original disk was smaller than we thought? What if it ended at only about 30 AU or so? In that case, Neptune would have migrated as far as it could, then stopped because there was nothing more to push against. The region beyond the disk's edge would have remained relatively empty, never accumulating enough material to form large Kuiper Belt objects. This scenario could explain the Kuiper cliff. The belt ends not because something removed objects from that region, but because there was never much material there to begin with. The primordial disk was compact, and everything beyond it remained a cosmic desert. Recent observations support some version of this idea. The Kuiper Belt we observe today contains far less mass than models predicted. Original estimates suggested the belt should contain 100 times as much material as we actually see. Where did it all go? Some of it was scattered outward by Neptune, populating the scattered disk and contributing to the Oort cloud. Some was scattered inward, becoming centaurs and short-period comets that eventually burned up near the Sun. And some might never have existed in the first place if the original disk was smaller than assumed. But there is a problem with this explanation. Even if the original disk was compact, the region beyond Neptune's reach should have been populated by objects scattered outward during the migration. These objects would have high eccentricities and inclinations, but they should exist, and we are finding evidence that they do. The discoveries from the New Horizons mission and the Subaru telescope surveys suggest that objects exist well beyond 50 AU. The dust detected by New Horizons implies ongoing collisions, which requires a population of bodies to do the colliding. Something is out there, even if it is harder to see than the classical belt. Perhaps the Kuiper cliff is not as sharp as it appeared. Perhaps it represents a decline in density rather than a true edge, a transition zone between the main belt and a more diffuse outer region. As our telescopes improve and our surveys go deeper, we may find that the belt continues far beyond what we currently map. This is an exciting possibility because it changes our understanding of the solar system's extent. For decades, we thought of the Kuiper Belt as a well-defined structure with clear boundaries. Now we are realizing that it might be more like the outer edge of a spiral arm, gradually fading into the darkness of interstellar space rather than ending abruptly. The extended Kuiper Belt, if it exists, would connect to another long-theorized structure, the inner Oort cloud, sometimes called the Hills cloud after astronomer Jack Hills, who first proposed it. The Oort cloud is the most distant region of the solar system, a spherical shell of icy bodies extending perhaps 100,000 AU from the Sun. Halfway to the nearest star, it is thought to contain trillions of comet nuclei, gravitationally bound to the Sun, but easily disturbed by passing stars or the galactic tide. But between the Kuiper Belt at 50 AU and the Oort cloud at thousands of AU, there must be something. This intermediate region, the inner Oort cloud, would contain objects scattered from the original belt, but not quite distant enough to be randomly oriented by external perturbations. The Sednoids might be members of this inner Oort cloud. Their orbits are elongated enough to take them far from the Sun, but their orientations still reflect the plane of the solar system. They are transitional objects, caught between the structured belt and the chaotic cloud. If a massive object lurks in the outer solar system, whether planet, black hole, or something else, it would orbit in this intermediate zone. Its gravitational influence would shape the inner edge of the Oort cloud, determining which objects remain detached and which get scattered further. This perspective helps explain why the search for Planet 9 is so difficult. We are not looking for something in the relatively well-mapped Kuiper Belt. We are searching the vast, empty spaces between known structures where distances are measured in hundreds of astronomical units and travel times in tens of thousands of years. Even at the speed of New Horizons, one of the fastest spacecraft ever launched, it would take decades to reach the region where Planet 9 is predicted to orbit. Direct exploration of this realm remains beyond our current capabilities. For now, we can only watch and calculate, studying the gravitational echoes of whatever hides in the darkness. But those echoes are getting clearer. With each new discovery, each new orbit calculated, we learn more about what is shaping the outer solar system. The pattern of clustering becomes more defined. The statistical evidence grows stronger. Something is out there. The question remains, what is it? Let us explore the candidates in more detail, weighing the evidence for and against each possibility. The leading candidate is still Planet 9, a super Earth-sized world on a distant, eccentric orbit. The evidence in its favor includes the clustering of extreme trans-Neptunian objects, the existence of high-inclination objects that are difficult to explain otherwise, and the population of Neptune-crossing objects whose orbits suggest external shepherding. Batygin and Brown have refined their estimates over the years. Current models suggest Planet 9 has a mass of about 5 to 7 times that of Earth, significantly less than early estimates of 10 to 15 Earth masses. its orbital distance has also been revised, with recent calculations placing it around 300 AU, rather than the original 400 to 800 AU. These revisions make Planet 9 easier to detect but also easier to hide. A smaller planet is fainter, but a closer planet should be brighter. The net effect is uncertain. What is clear is that if Planet 9 exists within current estimates, the Vera Rubin Observatory should be able to find it. The composition of Planet 9, if it exists, would likely be similar to the ice giants Uranus and Neptune. It would have a thick atmosphere of hydrogen and helium, surrounding a core of rock, ice, and perhaps liquid. Its surface would be impossibly cold, barely warmer than interstellar space itself, but new research published in 2025 suggests that Planet 9 might actually be more rocky than icy. Detailed simulations of planet formation in the outer solar system show that objects of this mass could have a range of compositions depending on where and how they formed. If Planet 9 formed closer to the Sun and was ejected outward, it might be denser and smaller than an ice giant of the same mass. This has implications for detectability. A rocky super-Earth would be smaller than an icy mini-Neptune of the same mass, making it fainter and harder to find. But it would also have different thermal properties, potentially affecting its infrared signature. The main argument against Planet 9 is simple. We have not found it. After nearly a decade of searching, covering the majority of the predicted search area, no planet has been detected. Every year that passes without a discovery makes the hypothesis slightly less likely, though it cannot rule it out entirely. The planet could be hiding in the remaining unsearched regions, or it could be fainter than predicted. The primordial black hole hypothesis offers an elegant alternative. A black hole of the same mass would produce identical gravitational effects while remaining completely invisible to conventional telescopes. This would explain why exhaustive searches have failed to find anything. The evidence in favor of this hypothesis is largely theoretical. Primordial black holes are predicted by cosmological models, and some observational hints suggest they might exist in masses relevant to the outer solar system. The Ogle microlensing survey detected an unexplained population of objects with masses similar to what Planet 9 would have. But the evidence against is also significant. Primordial black holes have never been directly confirmed to exist. While they are theoretically possible, their formation requires specific conditions in the early universe that remain uncertain. Furthermore, a black hole in the outer solar system would need to have been captured during the Sun's formation, which requires additional unlikely circumstances. The proposed detection method, looking for flares from tidally disrupted comets, is clever but uncertain. We do not know how many objects would pass close enough to the black hole to produce detectable flares, or whether our instruments would be sensitive enough to see them against the background of other transient events. Still, the black hole hypothesis cannot be ruled out. It remains a viable explanation that deserves serious consideration. If Planet 9 searches continue to come up empty, even after Rubin Observatory completes its survey, the black hole hypothesis will become more attractive. A third possibility is that there is no massive object at all. The observed clustering might be a statistical artifact, the result of observational biases and small sample sizes. When you are searching the sky for faint distant objects, you cannot look everywhere equally. Some regions are easier to observe than others, and this creates patterns in the data that might not reflect real structures in space. Critics of the Planet 9 hypothesis have pointed out that the extreme trans-Neptunian objects were discovered by different surveys looking in different directions at different times. combining data from disparate sources introduces potential biases that are hard to quantify. If certain orbits are easier to detect than others, the apparent clustering might be an illusion. Several studies have attempted to assess whether observational bias can explain the clustering. The results are mixed. Some analyses find that bias could account for much of the effect. Others find that the clustering remains significant even after correcting for known biases. The strongest argument against the bias explanation is that the clustering keeps showing up as more objects are discovered. If it were purely a bias effect, adding new data points from different surveys should dilute the pattern. Instead, the clustering has gotten stronger over time, with the latest analyses reporting 5 sigma significance, the gold standard for scientific discoveries. But 5 sigma does not mean certainty. It means that the probability of the pattern arising by chance is about 1 in a million. Given how many patterns astronomers look for in how many data sets, some apparent discoveries will turn out to be flukes. The history of science is littered with 5 sigma claims that later evaporated. The only way to resolve the debate is to find the object or conclusively rule it out. That is why the upcoming Rubin Observatory survey is so crucial. It will provide an independent, comprehensive data set that should either confirm the clustering with overwhelming evidence or reveal it to be an artifact. Beyond these 3 main candidates, more exotic possibilities have been proposed. Some researchers have suggested that the clustering is caused by the collective gravity of the Kuiper Belt itself, rather than a single massive object. If the belt contains more mass than we observe, distributed in a particular way, it could create gravitational perturbations that mimic the effect of a planet. This idea connects to the missing mass problem. We see far less material in the Kuiper Belt than our models predict. Perhaps that mass exists, but is distributed in smaller, fainter objects that we have not detected yet. Or perhaps it exists in a different form entirely, such as a diffuse disk of dust and ice that would be hard to observe directly. The extended belt detected by New Horizons lends some support to this idea. If significant mass exists beyond 50 AU, it could contribute to the gravitational effects we attribute to Planet 9. But preliminary calculations suggest that the additional mass needed would be substantial, perhaps comparable to Earth's mass spread over a vast region. Creating such a structure would require specific conditions during the solar system's formation, and maintaining it for billions of years would require the absence of perturbing influences. Neither condition is easy to satisfy. Most models suggest that any primordial mass in this region would have been scattered or accreted long ago. Still, the idea cannot be dismissed entirely. Our understanding of the outer solar system remains incomplete, and there may be structures we have not imagined yet. Another exotic possibility involves modifications to gravity. We have already mentioned MOND, which proposes that gravity behaves differently at very low accelerations. But other modifications are possible as well. Some theories of dark matter predict that it clumps in ways that could affect planetary orbits. If the solar system passed through a dense region of dark matter, or if dark matter formed structures called mini-halos, their gravitational effects might influence distant objects. Most dark matter models predict that these effects would be too weak to explain the observed clustering. But our understanding of dark matter remains limited. It constitutes about 27% of the universe's mass energy content. Yet, we have never directly detected a dark matter particle. There could be surprises lurking in the physics of the dark sector. The most speculative possibility is that the clustering is evidence for new physics entirely. Perhaps there is something about gravity, space, or time that we do not understand, something that becomes apparent only at the extreme distances and timescales of the outer solar system. This is the kind of idea that scientists treat with extreme caution. Proposing new physics to explain an observation is a last resort, invoked only when all conventional explanations have failed. We are nowhere near that point with the Kuiper Belt anomalies, but it is worth remembering that the universe has surprised us before, and it will surprise us again. For now, the balance of evidence points towards something massive in the outer solar system, whether planet, black hole, or some other object. The exact nature of this object remains unknown, but we are closer than ever to finding out. The search for whatever hides in the Kuiper Belt is not just about finding a new object. It is about understanding the fundamental architecture of our solar system and, by extension, planetary systems throughout the universe. When we look at other stars, we see an incredible diversity of planetary arrangements. Some systems have giant planets hugging close to their host stars, scorchingly hot and tidally locked. Others have super-Earths in their habitable zones, worlds that might harbor oceans of liquid water. Still others appear to have vast debris disks extending far beyond any detected planets, hinting at structures we have never observed up close. Our own solar system, once considered typical, now looks increasingly unusual. Most sun-like stars seem to host at least one planet between the mass of Earth and Neptune. These super-Earths, or mini-Neptunes, are the most common type of planet in the galaxy, yet our solar system has none, at least among the known planets. This is the missing super-Earth problem, and Planet 9 might be the solution. If a massive planet orbits in the outer solar system, it would fill the gap in our planetary census. We would not be strange for lacking a super-Earth. We would simply have one in an unexpected location. But how could a super-Earth end up so far from the Sun? Planets form from the disk of gas and dust that surrounds a young star. The material closer to the star is hotter and contains more rock and metal. The material farther out is colder and contains more ice. At very large distances, the disk is too sparse and cold for planets to form efficiently. Standard models of planet formation suggest that super-Earths should form at distances of a few astronomical units to a few tens of astronomical units, not hundreds. Getting a planet to its predicted location would require some additional process. One possibility is that Planet 9 formed closer to the Sun and was ejected outward by gravitational interactions with the gas giants. In the chaotic early days of the solar system, close encounters between planets were common. Jupiter's immense gravity could have flung a smaller planet outward, where it settled into a distant orbit rather than escaping entirely. This scenario fits with the Nice model of planetary evolution. The model includes a period of instability when the giant planets migrated and interacted strongly with each other and with a massive disk of planetesimals. Some versions of the Nice model even include a fifth giant planet that was ejected from the solar system. Perhaps Planet 9 is a surviving remnant of that chaotic era, not quite ejected, but pushed to the very edge. Another possibility is that Planet 9 was captured from interstellar space. Stars form in clusters, and young stellar systems pass close to each other relatively often. During these close encounters, material can be exchanged between systems. A planet formed around another star could have been gravitationally captured by our Sun, becoming an adopted member of our solar system. The probability of such capture is low, but not negligible. Simulations suggest that perhaps 1% of Sun-like stars might capture a rogue planet during their lifetime. If Planet 9 is a captured world, It would provide direct evidence that planetary exchange occurs between stellar systems. The capture scenario has an interesting connection to the primordial black hole hypothesis. If primordial black holes exist in significant numbers, they would also wander through interstellar space, occasionally encountering stellar systems. The probability of capturing a black hole would be similar to the probability of capturing a rogue planet of the same mass. So whether we find a planet or a black hole in the outer solar system, it could have originated beyond our star. The object might carry chemical signatures from its original formation environment, signatures that differ from anything else in our solar system. Analyzing such a world would tell us about conditions around other stars, even without leaving our own cosmic neighborhood. A third possibility is that Planet 9 formed in place, far from the Sun, through a process called pebble accretion. In this scenario, small particles in the outer solar system slowly drift inward, losing energy to gas drag. If a seed object exists at the right location, these pebbles can pile up on it, gradually building a larger body. Pebble accretion has been proposed to explain the formation of the ice giants Uranus and Neptune. These planets are hard to form through traditional collisional growth because the outer solar system is so vast and sparse. Objects rarely encounter each other, making it difficult to build up large bodies through mergers. But pebble accretion solves this problem by delivering material from a wide region to a localized nucleus. The process is efficient enough to form ice giant-sized planets even at distances of tens of astronomical units. Could it work at hundreds of AU as well? The answer depends on conditions in the early solar disk. If the disk extended far enough and contained sufficient material, a distant planet could have grown through pebble accretion. The resulting world would be primarily icy, similar to Uranus and Neptune but smaller. However, recent research suggests that the outer regions of protoplanetary disks are often too sparse for significant pebble accretion. The process requires a minimum amount of material flowing through the formation region, and this threshold may not have been met at very large distances from the Sun. The debate about Planet 9's origin highlights how much we still have to learn about planet formation. Every scenario we consider reveals gaps in our understanding, physical processes that we have not fully characterized, or conditions that we cannot constrain observationally. Finding Planet 9, or whatever lurks in the outer solar system, would provide crucial data. By measuring its mass, composition, and orbit, we could work backward to understand how it formed and what it tells us about the early solar system. And that is just the beginning. If we confirm that massive objects can exist in distant orbits around Sun-like stars, it would have profound implications for exoplanet research. Currently, our methods for detecting exoplanets work best for planets relatively close to their host stars. The radial velocity technique detects the wobble that an orbiting planet induces in its star. The transit technique detects the dimming when a planet passes in front of its star. Both methods require the planet to have a significant effect on its star, which is easier if the planet is close. Detecting a distant super-Earth orbiting another star is nearly impossible with current technology. The planet would induce only a tiny wobble over a decade-long orbit. It would rarely transit, and if it did, it would block only a negligible fraction of the star's light. This means we have essentially no data on whether other stars host distant giant planets. We know about hot Jupiters and warm Neptunes and compact multi-planet systems, but the outer regions of exoplanetary systems remain terra incognita. If Planet 9 exists, it suggests that distant super-Earths might be common. hidden beyond our detection limits around countless other stars. The solar system would not be unusual for having such a planet. It would simply be the first place we found one because we could study the gravitational effects on smaller bodies. This perspective changes the way we think about planetary systems. They might be larger and more complex than the data show. The planets we detect might be just the inner core of systems that extend far beyond, teeming with worlds we cannot see. Of course, the opposite might also be true. If exhaustive searches fail to find Planet 9, it would suggest that distant super-Earths are rare. Perhaps most planetary systems are compact, with all significant mass concentrated within a few tens of AU. Our solar system would be typical in this respect, and the clustering of extreme trans-Neptunian objects would need a different explanation. Either result would be scientifically valuable. We learn from confirmations and refutations alike. The search for Planet 9 is not a gamble that might come up empty. It is an investigation that will yield insights regardless of outcome. This is the nature of exploration. We venture into the unknown, not knowing what we will find. Sometimes we discover what we expected. Sometimes we find something completely different. Sometimes we return with questions instead of answers, but we always learn. The outer solar system has been unknown territory for most of human history. Even after the discovery of Neptune in 1846, the region beyond remained shrouded in darkness. Pluto's discovery in 1930 provided a glimpse, but a limited one. Only in the past few decades have we begun to map this realm in earnest. And what we have found has consistently surprised us. We expected the Kuiper Belt to be uniform and sparse. Instead, it has structure and complexity, populations and subpopulations, gaps and cliffs. We expected the giant planets to have formed in their current orbits. Instead, they migrated and interacted, reshaping the outer solar system. We expected to understand the basic architecture of our cosmic home. Instead, we found mysteries within mysteries. The search for what hides in the Kuiper Belt continues this tradition of discovery. Whatever we find will challenge our assumptions and expand our horizons. That is what exploration means. Let us now turn to the practical aspects of the search. How are astronomers looking for Planet 9? And what have they found so far? The most straightforward approach is direct imaging. If Planet 9 reflects enough sunlight, it should appear as a faint point of light moving slowly against the background stars. The challenge is that it would be incredibly faint, perhaps magnitude 22 or fainter, and moving only a few arcseconds per day. To put this in perspective, magnitude 22 is about 10 million times fainter than the dimmest star visible to the naked eye. Even with large telescopes, detecting such a faint object requires long exposures and careful data processing. And because the object is moving, you cannot simply stack multiple exposures to build up signal. The object would smear out, becoming even harder to see. The solution is a technique called shift and stack. Astronomers take a series of images over several hours, then digitally shift each image to account for the predicted motion of a distant object. By stacking the shifted images, they can build up signal for a moving object, while the stationary background stars become blurred. The difficulty is that you have to know which way the object is moving to shift the images correctly. If you guess wrong, you will not see anything. And if Planet 9 could be anywhere in a large region of sky, moving in many possible directions, you have to try many different shifts for every region you observe. This is computationally intensive. A single night of observations produces terabytes of data. and searching that data for faint moving objects requires millions of shift and stack operations. Advanced algorithms and powerful computers have made this feasible, but it remains a slow, painstaking process. Several teams have conducted extensive searches for Planet 9 using this approach. Mike Brown and Konstantin Batygin at Caltech have spent years scanning the predicted search region with the Subaru telescope in Hawaii and other instruments. Chad Trujillo and Scott Shepard, who discovered 2012 VP113, have conducted their own surveys with the Dark Energy Camera in Chile. Other groups have taken different approaches. The WISE and NEOWISE space telescopes surveyed the entire sky in infrared wavelengths, searching for the faint heat signature that a cold planet would emit. At the temperatures expected for Planet 9, around 50 Kelvin, the planet would radiate primarily at mid-infrared wavelengths. WISE should have been able to detect it if it were large enough and close enough, but found nothing conclusive. More recently, researchers have analyzed data from the IRAS and Akari space missions, looking for moving sources between observations taken decades apart. A 2025 paper reported a possible detection in the constellation Eridanus, but the result remains unconfirmed and controversial. Citizen science projects have also contributed to the EVIDE search. NASA's Backyard Worlds project invites volunteers to examine images from WISE, looking for moving objects that automated algorithms might have missed. Hundreds of thousands of participants have examined millions of images, discovering several hundred brown dwarfs and other faint objects, though not yet Planet 9. Despite all this effort, Planet 9 remains undetected, but that doesn't mean the search has failed. It has successfully ruled out the planet's presence in most of the predicted search region. Brown and Batygin estimate that about 78% of the region where Planet 9 could orbit has been eliminated. That leaves 22%, a still substantial area of sky. And as the predicted parameters for Planet 9 have been refined, the search region has shifted. Earlier predictions placed the planet farther out and more massive. Newer models suggest it might be smaller and closer, which changes where astronomers should look. The Vera Rubin Observatory represents the next great hope for the search. This new facility in the mountains of Chile combines a large mirror with an enormous field of view camera, allowing it to survey vast swaths of sky quickly and deeply. The Legacy Survey of Space and Time, Rubin's 10-year observing program, will image the entire visible sky every few nights. By comparing images taken at different times, researchers will be able to identify anything that moves. The survey's depth and coverage should be sufficient to detect Planet 9 if it exists within current predictions. Brown and Batygin have stated that Rubin should either find Planet 9 or conclusively rule it out within a year or two of beginning operations. That timeline puts us on the verge of resolution. After nearly a decade of uncertainty, we may soon know whether a ninth planet orbits our Sun. But what if Rubin does not find a planet? What then? The absence of a planet detection would not automatically vindicate the black hole hypothesis or any other alternative. It would simply mean that whatever causes the clustering is harder to see than a predicted super-Earth. We would need to reconsider the evidence, revise our models, and perhaps accept that the mystery remains unsolved. One possibility is that Planet 9 exists, but is fainter than expected. If it is smaller, more distant, or lower albedo than current predictions, it might escape detection even by Rubin. The search would need to continue with future instruments, pushing to fainter magnitudes and larger areas of sky. Another possibility is that the Clustering is indeed caused by a black hole. In that case, Rubin might still provide evidence through the detection of accretion flares. Loeb and Siraj have calculated the expected rate of such flares, and while it is uncertain, there is a reasonable chance that Rubin could spot one or more during its survey. A third possibility is that the clustering results from some phenomenon we have not yet considered. Perhaps the explanation is more mundane than a missing planet, or perhaps it is more exotic than a black hole. Science often progresses by eliminating wrong ideas until the right one remains. The point is that the search continues regardless of any single result. We are not hunting for Planet 9 because we know it exists. We are investigating an anomaly in our understanding of the outer solar system. That anomaly is real, supported by evidence that has grown stronger over time. Whatever explains it will teach us something new. And that is the essence of scientific exploration. We follow the evidence where it leads, not where we expect it to go. The outer solar system is full of surprises, and we are still discovering what they are. As we approach the end of our journey tonight, let us reflect on what we have learned and what still remains hidden. The Kuiper Belt is not the simple ring of debris we once imagined. It is a complex, structured realm with distinct populations, mysterious gaps, and objects on orbits that defy explanation. The Kuiper Cliff marks an abrupt boundary that our models cannot explain. The sednoids follow paths that no known gravitational influence can produce. Something massive appears to be shaping this region. The clustering of extreme trans-Neptunian objects points to an unseen perturber, herding distant bodies into aligned orbits. The statistical evidence for this clustering has grown steadily stronger, reaching levels that would normally be considered decisive. Yet the perturber itself remains undetected. Years of searching have failed to image a distant planet. The most likely explanation remains a super-Earth on a distant orbit, the hypothetical Planet 9. But alternatives exist. A primordial black hole, a relic from the earliest moments of cosmic history, could produce identical gravitational effects while remaining invisible. More exotic possibilities have been proposed as well. A concentrated disk of material, modifications to gravity, the lingering influence of a planet long since ejected. Each explanation has strengths and weaknesses, and none can yet be ruled out. What we can say with confidence is that our picture of the outer solar system is incomplete. There are objects and structures we have not discovered, physical processes we have not characterized, and histories we have not reconstructed. The darkness beyond Neptune holds secrets that we are only beginning to glimpse. The coming years promise resolution of at least some of these mysteries. The Vera Rubin Observatory will survey the sky with unprecedented depth and coverage, searching for anything that moves in the distant darkness. If Planet 9 exists within current predictions, Rubin will find it. If it does not, we will know that as well, and can revise our hypotheses accordingly. Meanwhile, New Horizons continues its journey outward, probing the structure of the outer belt and the heliosphere beyond. Its measurements of dust and radiation provide ground truth for our telescopic observations, revealing features too subtle to see from Earth. Future missions may eventually follow. Concepts have been proposed for spacecraft that would journey to the outer solar system, perhaps even to Planet 9 if it is discovered. Such missions would take decades, but would provide information that no telescope can match. Direct observation of a distant giant planet would transform our understanding of planetary science. For now, we watch and wait and wonder. What lurks at the edge of our solar system? What shape the strange orbits we observe? What will we find when we finally peer into the darkness? These questions have occupied human minds since we first looked up at the night sky and wondered what lay beyond. The ancient Sumerians charted the wandering stars and gave them names. The Greeks developed geometrical models of celestial motion. The Renaissance astronomers built telescopes and discovered new worlds. Each generation has pushed the boundary of the known a little further outward. We are the inheritors of that tradition. The outer solar system is our new frontier, as the planets were for Galileo and the stars were for Hubble. We explore it not because we expect easy answers, but because the questions themselves are worth asking. So let your mind drift outward, past the blue globe of Earth, past the red sands of Mars, past the swirling storms of Jupiter and the shimmering rings of Saturn. Keep going, past the tilted ice worlds of Uranus and Neptune, into the cold and the dark where sunlight fades to a dim memory. There, in that eternal twilight, something waits. We do not yet know what it is. A frozen giant, a collapsed fragment of primordial time, or something stranger still. But it is there shaping the trajectories of distant worlds, leaving its fingerprints on orbits that take 10,000 years to complete. Someday we will find it. Someday we will give it a name and place it on our maps. And when we do, a new mystery will surely take its place, beckoning us further into the unknown. That is the nature of exploration. That is the promise of the cosmos. The universe is vast beyond imagination, and we have only begun to discover what wonders it holds. The study of the outer solar system connects to some of the deepest questions in astronomy. How do planetary systems form? How do they evolve over billions of years? What determines which configurations are stable and which are not? By understanding our own solar system in detail, we gain insights that apply to worlds orbiting distant stars. Consider the formation of the giant planets. Jupiter and Saturn, the gas giants, are composed primarily of hydrogen and helium, the same elements that make up the Sun. They formed quickly within the first few million years of the solar system's history, while the primordial gas disk still surrounded the young Sun. To accumulate so much gas, Jupiter and Saturn needed large rocky cores first. These cores, perhaps 10 to 20 times the mass of Earth, formed from the collision and merger of smaller bodies. Once the cores reached a critical mass, they began pulling in gas from the surrounding disk, growing rapidly until the disk dissipated. Uranus and Neptune, the ice giants, have a different composition. They contain substantial amounts of water, ammonia, and methane in addition to hydrogen and helium. Their formation was slower, occurring after much of the gas had already dispersed. They grew primarily through the accumulation of solid material, ice-rich planetesimals from the cold outer regions of the disk. This difference in composition reflects a difference in location and timing. Jupiter and Saturn formed in regions with abundant gas, close enough to the Sun for the disk to be relatively dense. Uranus and Neptune formed farther out, where the disk was sparser and gas had already begun to escape. But here is the puzzle. Uranus and Neptune are so far from the Sun that forming them through traditional accretion seems almost impossible. At 20 and 30 astronomical units, the orbital periods are 84 and 165 years respectively. Objects in these regions encounter each other very rarely. Building up Earth mass cores through collisions would take longer than the age of the solar system. This is the ice giant formation problem, and it has driven major revisions in our understanding of how the outer solar system came to be. The NICE model addresses it by proposing that Uranus and Neptune formed closer to the Sun, perhaps between 15 and 20 AU, and migrated outward later. In this scenario, their formation was more efficient because they started in a denser region of the disk. The migration was driven by interactions with the primordial planetesimal disk. As the ice giants scattered small bodies, Newton's third law ensured that they felt a reaction force. Over millions of years, these tiny pushes added up, gradually moving the planets outward. This migration had profound consequences. As Neptune moved outward, it swept through the primordial Kuiper Belt, scattering most objects and trapping others in orbital resonances. The resonant populations we observe today, the Plutinos and Tutinos and others, are the survivors of this gravitational sieve. Some scattered objects went inward, becoming centaurs that orbit between the giant planets, and eventually short-period comets that visit the inner solar system. Others went outward, populating the scattered disk and contributing to the Oort cloud. A few were lifted to high perihelia, becoming detached objects like Sedna that no longer interact with Neptune. The NICE model explains many features of the outer solar system, but it also has limitations. It struggles to reproduce all the details of the Kuiper Belt structure. It cannot easily account for the cold classical population, which seems too dynamically pristine to have survived the migration upheaval. And it does not explain why some objects have the extreme orbits we observe among the sednoids. This is where a massive perturber comes in. If a large planet existed in the outer solar system, during or shortly after the migration epoch, its gravity could have influenced the trajectories of scattered objects. It could have lifted perihelia, created clustering patterns, and imprinted the primordial alignment that we see today in the sednoid orbits. The question is, what happened to this perturber? Did it remain in place, becoming the planet 9 we now seek? Or was it ejected from the solar system, leaving only its gravitational ghost behind? Both scenarios are physically plausible. The NICE model already includes mechanisms for ejecting planets. In some simulations, a fifth giant planet forms along with the others and is later scattered out of the solar system by encounters with Jupiter or Saturn. This ejected planet would carry away some orbital energy and angular momentum, helping to stabilize the remaining planets in their current orbits. If this ejection happened early enough, the perturber's influence on the Kuiper Belt would be frozen in place. The clustering it created would persist, gradually randomizing over billions of years, but never completely disappearing. We would see the remnants of that ancient event in the orbits of extreme trans-Neptunian objects today. Alternatively, if the perturber survived but was pushed to a distant orbit rather than ejected entirely, it would continue influencing the outer solar system to the present day. Its gravity would maintain the clustering, keeping the sednoid orbits aligned against the background tendency toward randomization. Distinguishing between these scenarios requires more data. If Planet 9 exists and is found, we can measure its current orbit and work backward to understand its history. If no planet exists, we can conclude that the perturber was ejected and that what we observe is a fossil of the early solar system. Either result would be profound. A present-day Planet 9 would be a laboratory for studying distant super-Earths, providing detailed information about a class of planets that dominates the galaxy, but has never been observed up close. An ejected planet would be evidence that our solar system was once more complex, with an additional giant world that has long since departed for interstellar space. The broader context here is that planetary systems are dynamic. They do not form in their final configurations and remain unchanged. Planets migrate, they interact, they scatter objects and occasionally each other. Over billions of years, chaotic processes reshape what started as an orderly structure. This perspective applies to exoplanetary systems as well. When we observe a hot Jupiter orbiting within days of its host star, we know it did not form there. The temperatures were too high for ice to condense, and without ice, not enough solid material existed to build a giant planet core. The hot Jupiter must have formed farther out and migrated inward, perhaps pushed by interactions with a disk or pulled by gravitational encounters with other planets. Similarly, when we see tightly packed systems of super-Earths, we suspect that migration played a role. The planets may have formed at larger separations and converged as they interacted with the gas disk. Their current compact configuration reflects the endpoint of a migration process, not their birth positions. And when we see gaps in debris disks around other stars, we wonder whether hidden planets are responsible. A massive planet would gravitationally clear material from its orbit, creating a gap or ring structure in the surrounding dust. The details of the gap can tell us about the planet's mass and location, even if we cannot see the planet directly. These techniques have already been applied to many young stellar systems. Rings and gaps in debris disks are common, suggesting that planet formation is widespread. Some systems have directly imaged giant planets orbiting at tens or hundreds of AU, proving that massive worlds can exist at great distances from their stars. Our solar system fits into this broader picture. The Kuiper Belt is our debris disk, a remnant of the material that did not become planets. The Kuiper Cliff may be evidence of a planet that cleared its orbit long ago. The clustering of extreme trans-Neptunian objects suggests an ongoing gravitational influence, whether from a present-day planet or the memory of one that departed. By studying these features in detail, we contribute to the general understanding of how planetary systems work. Our solar system is not just our home. It is a case study, a natural laboratory, where we can investigate processes that shape worlds throughout the galaxy. This is one reason why the search for Planet 9 matters beyond simple curiosity. Finding or ruling out a distant super-Earth would inform models of planet formation and evolution. It would constrain theories of disk dynamics and planetary migration. It would provide context for interpreting observations of other stellar systems. Science progresses through the interplay of theory and observation. We build models to explain what we see, then test those models by looking for what they predict. The outer solar system is rich with predictions: a missing planet, a possible black hole, an extended belt of material, structures shaped by ancient gravitational encounters. Each of these predictions can be tested, and each test teaches us something new. The search also drives technological advancement. The techniques developed to find faint moving objects in deep surveys have applications beyond Planet 9. They can detect asteroids that might pose a collision threat to Earth. They can identify distant dwarf planets and Kuiper Belt objects worthy of future study. They can spot transient events like supernovae and gravitational wave counterparts. The Vera Rubin Observatory, built partly with Planet 9 in mind, will revolutionize many areas of astronomy. Its survey will discover millions of asteroids, thousands of distant supernovae, and countless variable stars. It will track near-Earth objects, measure the expansion of the universe, and probe the nature of dark energy. Planet 9 is just one of many discoveries it might make. This kind of serendipity is common in exploration. We set out to find one thing and discover something else entirely. Columbus sought a route to Asia and found the Americas. Astronomers searching for Neptune found Triton, its largest moon, just 17 days later. The Hubble Space Telescope, designed to study distant galaxies, has returned iconic images of every planet in our solar system. So even if Planet 9 does not exist, the search will not have been wasted. The data collected, the techniques developed, and the understanding gained will have lasting value. Science is not a treasure hunt where you either find the prize or go home empty-handed. It is a process of accumulating knowledge, and every step forward, even the ones that lead to dead ends, contributes to the whole. Now let us consider a different aspect of the mystery, the timescales involved. When we talk about the outer solar system, we are dealing with periods that dwarf human experience. Sedna's orbital period is 11,000 years. It has not completed a single orbit since the end of the last ice age. The people who painted the caves at Lascaux would have seen Sedna in roughly the same position where it is today, slowly creeping along its path around the Sun. Planet 9, if it exists with the predicted parameters, would have an orbital period of 10 to 20,000 years. That means it has completed only 2 to 400 orbits since the solar system formed. In the time it takes Planet 9 to go around the Sun once, human civilization could rise and fall a dozen times. These timescales make the outer solar system a fundamentally different environment from the inner planets. Here, where we live, orbital periods are measured in days or years. We can watch Mercury race around the Sun 4 times in an Earth year. Even Jupiter, the largest planet, completes an orbit in just under 12 years. But out there in the cold darkness beyond Neptune, everything happens slowly. Objects drift along their orbits like glaciers, imperceptibly moving against the background of stars. The gravitational influences that shape their paths operate over millions of years, not months or decades. This slowness is both a curse and a blessing for astronomers. It is a curse because we cannot simply wait and watch things happen. We cannot observe the orbital clustering develop or the resonances form. We see only a snapshot, a single frame in a film that has been playing for 4.5 billion years. But it is a blessing because the outer solar system preserves information. In the inner solar system, things are constantly being reshuffled. Asteroids collide and fragment. Comets evaporate. Orbits are perturbed by the giant planets. The current configuration bears only faint traces of the initial conditions. In the outer solar system, change is slower. Objects that were scattered into certain orbits billions of years ago are still in those orbits today. The clustering we observe is a record of ancient events, written in the language of orbital mechanics and preserved by the vacuum of space. This is why astronomers describe Kuiper Belt objects as cosmic fossils. They carry information from the earliest days of the solar system, frozen in their compositions and their orbits. By studying them, we can reconstruct what happened during planet formation. Even though we were not there to see it, the sednoids are particularly valuable in this regard. Their orbits are so distant that they have been essentially unchanged for billions of years. Whatever event put them on their current paths, whether a rogue planet, a passing star, or something else, left a permanent mark. They are witnesses to the early solar system, and we are just learning to read their testimony. The same is true of the primordial alignment that some researchers have identified in the sednoid orbits. If all the known sednoids were more tightly clustered 4.5 billion years ago, that clustering must have been created by some event at that time. The subsequent randomization tells us about the rate of orbital evolution. while the initial alignment tells us about the event itself. This kind of forensic astronomy is one of the most exciting aspects of studying the outer solar system. We are not just cataloguing objects. We are reconstructing history, piecing together the story of how our cosmic neighborhood came to be. And the story is more dramatic than we might have expected. The NICE model paints a picture of a solar system in turmoil, with giant planets migrating, gravitational interactions flinging objects in all directions, and possibly a planet or two ejected into the void. The outer solar system we see today is the aftermath of that chaos, the survivors of a gravitational cataclysm that reshaped everything. If Planet 9 or a primordial black hole exists, it would add another chapter to this story. It would be evidence of capture or survival, a massive object that either entered the solar system from outside or managed to avoid ejection during the early instabilities. Its presence would have ongoing effects, continuing to shape the orbits of distant objects long after the initial chaos subsided. Understanding this history is not just an academic exercise. It helps us understand our own origins. The inner solar system, where Earth resides, was shaped by the same processes that affected the outer regions. The orbits of asteroids, the composition of comets, and the delivery of water and organic molecules to the early Earth all connect to the dynamics of the outer solar system. Some scientists have speculated that the same gravitational perturbations that scattered the Kuiper Belt also triggered the late heavy bombardment, a period roughly 4 billion years ago when the inner planets were pummeled by an intense barrage of asteroids and comets. This bombardment may have delivered water to Earth, creating the oceans that made life possible, or it may have sterilized the surface, wiping out any early life that had begun to emerge. Either way, the connection is profound. What happened in the outer solar system did not stay in the outer solar system. It affected everything, including the planet we call home. By studying the Kuiper Belt and whatever lurks within it, we learn about ourselves. This is the power of astronomy. It connects the largest scales to the smallest, the most distant past to the present moment. A frozen object billions of miles away carries information about events that shape the Earth and the life that inhabits it. The stars that appear as points of light in our night sky are nuclear furnaces forging the atoms that make up our bodies. We are part of the cosmos, not separate from it. The boundaries we draw between here and there, between us and the universe, are illusions. Everything is connected by gravity and light and the flow of matter through space and time. The search for Planet 9 is a chapter in this larger story. It is humanity reaching outward, asking questions about the darkness at the edge of our island in space. Whatever we find there will illuminate not just the solar system, but our place within it. Let us now journey deeper into the science of how we detect and characterize objects in the outer solar system. The methods astronomers use are ingenious, born of necessity when studying things too faint and far to see directly. The primary challenge is brightness. An object in the outer solar system receives very little sunlight, and it reflects only a fraction of what it receives. The total light reaching Earth from a typical Kuiper Belt object is astonishingly small. Even with the largest telescopes and most sensitive cameras, detecting these objects requires careful technique. The key is contrast. Stars appear as fixed points of light because they are so far away that even the fastest star does not perceptibly move across the sky during a human lifetime. Planets and asteroids, on the other hand, are much closer and do move against the stellar background. By taking multiple images of the same region of sky and comparing them, astronomers can identify anything that has shifted position. This technique works well for relatively bright, fast-moving objects. Asteroids in the main belt between Mars and Jupiter can be detected in pairs of images taken just minutes apart. Near-Earth asteroids, which approach our planet closely and therefore appear to move rapidly, can be spotted in even shorter time spans. But Kuiper Belt objects move slowly. At 50 astronomical units, an object's apparent motion against the stars might be only a few arcseconds per day. An arcsecond is 1/3600th of a degree, a tiny angle. To detect such subtle movement, astronomers must take images separated by hours or days, not minutes. This creates problems. Over longer time periods, conditions change. The atmosphere shifts, causing stars to twinkle and blur differently in successive images. The telescope might not point exactly the same way. Cosmic rays and electronic noise create spurious signals that must be distinguished from real objects. Sophisticated image processing techniques address these challenges. Software aligns images precisely, compensating for any telescope pointing errors. It identifies and removes cosmic ray hits. It models the point spread function, the way a point source of light spreads out due to atmospheric turbulence and optical imperfections, and uses that model to identify potential moving objects. The shift and stack technique mentioned earlier extends these methods to the faint limit. By digitally shifting images to track a hypothetical moving object, then stacking them to accumulate signal, astronomers can detect objects much fainter than would be visible in any single image. The challenge is knowing which direction to shift. For a general survey looking for unknown objects, astronomers must try many different shifts, covering the range of possible velocities. This is computationally intensive but feasible with modern hardware. The result is a set of candidate detections, each corresponding to a particular location and velocity. Most candidates turn out to be false alarms, artifacts of noise or image processing. Follow-up observations are needed to confirm real discoveries. An object must be detected on multiple nights, with positions that fit a consistent orbital trajectory, before it is considered confirmed. This process has yielded thousands of Kuiper Belt objects over the past 3 decades. Each discovery adds a data point to our map of the outer solar system. Collectively, they reveal the structure we have discussed: the resonant populations, the classical belt, the scattered disk, the detached objects, the sednoids. But finding a massive planet is different from finding a typical Kuiper Belt object. Planet 9, if it exists, would be much larger, but also much farther away. The net result is that it might not be much brighter than the smaller objects we have already found, and its greater distance means it moves even more slowly, making detection harder still. The predicted brightness of Planet 9 depends on assumptions about its size, distance, and reflectivity. Current estimates place it at around magnitude 20 to 24. That is faint, but not impossibly so. The challenge is the vast area of sky that must be searched. The predicted search region spans thousands of square degrees, a significant fraction of the sky visible from any single location. Covering this area with deep imaging requires years of telescope time. And because Planet 9's location is uncertain, the entire region must be monitored repeatedly, looking for subtle motion that would reveal a distant, slowly moving world. Several factors complicate the search. The Milky Way, our home galaxy, creates a bright band across the sky where the density of stars is highest. Searching this region for a faint moving object is like looking for a needle in a haystack. Planet 9 could be hiding behind the stellar crowds of the galactic plane. Additionally, Planet 9's brightness varies depending on where it is in its orbit. Near perihelion, when it is closest to the Sun, it would receive more sunlight and appear brighter. Near aphelion, when it is farthest, it would be dimmer. If Planet 9 is currently near aphelion, it might be 2 to 3 magnitudes fainter than the predictions assume, making it much harder to find. These uncertainties explain why the search has taken so long despite significant effort. Astronomers are not simply looking for an object they know exists. They are searching for something that might exist, with properties that can only be estimated, in a region that is difficult to observe. It is a hard problem. The Vera Rubin Observatory addresses many of these challenges. Its wide field of view allows it to survey large areas quickly. Its sensitivity reaches faint magnitudes that previous surveys could not achieve. Its cadence, with repeat observations every few nights, is well suited to detecting slowly moving objects. Rubin will observe the southern sky systematically over a decade. Even regions that are difficult to search, like areas with high stellar density, will receive attention. The resulting data set will be the most comprehensive survey of the sky ever conducted. If Planet 9 exists within the predicted parameter range, Rubin should find it. The search will either succeed, revealing a new world for humanity to explore, or it will set stringent limits on what can be hiding in the outer solar system. Either outcome advances our understanding. Beyond direct imaging, other techniques can probe the outer solar system. Stellar occultations occur when a solar system object passes in front of a distant star, briefly blocking its light. By carefully timing these events, astronomers can measure the size and even detect atmospheres of objects that are too small to image directly. Occultations have been used to study Kuiper Belt objects with remarkable precision. Pluto's atmosphere was characterized through occultations before New Horizons arrived. The ring around the dwarf planet Haumea was discovered through occultation observations. Even the tiny moon of Arakoth was revealed by an occultation event. For Planet 9, occultations offer a potential detection method if the planet's orbit can be sufficiently constrained. If we knew where to look with enough precision, we could predict when Planet 9 would occult a background star and attempt to observe the event. A successful detection would not only confirm the planet's existence, but provide an accurate position for follow-up imaging. However, occultation predictions require knowing where the object is, which is precisely what we do not know about Planet 9. The technique is more useful for characterizing a known object than for discovering an unknown one. Still, as the search region narrows, occultation monitoring may become a viable supplementary approach. Gravitational effects offer another window into the outer solar system. The positions of the known planets are measured with exquisite precision through radio tracking of spacecraft. Any perturbation from an undiscovered massive object would show up as a tiny deviation from the predicted orbits. NASA's Cassini spacecraft, which orbited Saturn for over a decade, provided the most precise measurements of Saturn's position ever obtained. These data have been used to constrain the possible locations of Planet 9. Certain orbital configurations would have produced detectable perturbations on Saturn that were not observed, allowing those configurations to be ruled out. The analysis is ongoing as more data accumulates. Each spacecraft that ventures to the outer solar system adds another data point. Juno at Jupiter, the proposed missions to Uranus or Neptune, all could contribute to the search by constraining where Planet 9 cannot be. However, gravitational detection has limitations. At the distances where Planet 9 is predicted to orbit, its gravitational influence on the known planets is extremely subtle. The perturbations would be measured in meters or less, at distances of billions of kilometers. Disentangling such tiny signals from other effects requires extraordinary precision and long observation baselines. The most promising gravitational approach focuses not on the planets, but on distant spacecraft. A probe heading into the outer solar system would feel the gravitational pull of any massive object along its path. By precisely tracking the spacecraft's trajectory, we might detect the signature of Planet 9. This was one motivation for proposals to send a dedicated mission to search for Planet 9. A small spacecraft with a radio transponder, launched on a trajectory through the predicted Planet 9 region, could survey for gravitational perturbations while also imaging candidate locations. Such a mission would be expensive and slow, taking years to reach the search region, but it would provide data inaccessible from Earth. For now, ground-based and space-based telescopes remain our primary tools. They have revealed the outer solar system in remarkable detail, discovering thousands of objects and characterizing the overall structure of the Kuiper Belt. The remaining mystery, what massive object might lurk beyond the belt's edge, is the next frontier. The implications of finding something massive in the outer solar system extend far beyond our own cosmic neighborhood. If Planet 9 exists, it would likely be a super-Earth or mini-Neptune, a type of planet that is extremely common throughout the galaxy, but entirely absent from the known solar system. Exoplanet surveys have revealed that super-Earths, planets with masses between that of Earth and Neptune, are the most common type of planet around other stars. Nearly every Sun-like star seems to host at least one, yet our solar system appears to have none, at least among the 8 known planets. This has puzzled astronomers. Did our solar system form differently than others? Was there some event that prevented super-Earths from forming or surviving in our system? Or do we simply have a super-Earth that we have not found yet? Planet 9 could be that missing super-Earth. If it exists, our solar system would not be anomalous after all. We would simply have our super-Earth in an unexpected location, far from the Sun in a highly eccentric orbit. Studying Planet 9 directly would provide invaluable information about this common class of planets. We could measure its mass precisely through observations of its gravitational effects on smaller bodies. We could determine its size and density, revealing whether it is rocky like Earth or icy like Neptune. We could potentially detect an atmosphere and characterize its composition. Such observations are impossible for exoplanets, which are so distant that they appear only as faint points of light, if they can be detected at all. Planet 9, though far by solar system standards, would be close enough for detailed study. It would become a Rosetta Stone for understanding super-Earths throughout the galaxy. The scientific community is eagerly awaiting the resolution of this mystery. Professional conferences feature sessions devoted to the search. Peer-reviewed journals publish new analyses regularly. Graduate students build careers around understanding the outer solar system's dynamics. This level of interest reflects both the scientific importance of the question and the tantalizing nature of the evidence. The clustering of extreme trans-Neptunian objects is real and statistically significant. Something is causing it. The debate is over what that something is, not whether the phenomenon exists. Some researchers remain skeptical. They point to the possibility that observational biases have been underestimated, that the apparent clustering is an artifact rather than a genuine signal. They note that years of searching have failed to find a planet, which they interpret as evidence against its existence. Others are more optimistic. They argue that the evidence has grown stronger over time, not weaker. New discoveries continue to support the clustering hypothesis. The statistical significance keeps increasing as more data accumulates, and the failure to find Planet 9 directly can be explained by its faintness and the vastness of the search region. The beauty of science is that this debate will be resolved by evidence, not argument. The Vera Rubin Observatory will provide data sufficient to settle the question one way or another. Either Planet 9 will be found, or its existence will be strongly constrained. The scientific community will reach a consensus based on what the observations reveal. Until then, the mystery remains open. Something massive appears to be hiding in the Kuiper Belt. Whether it is a planet, a black hole, or something else entirely, we do not yet know. But we are closer than ever to finding out. And so we reach the final moments of our journey tonight. We have traveled far, from the familiar warmth of Earth to the frozen darkness at the edge of everything we know. We have explored the Kuiper Belt, that ring of ancient ice and rock where the sun's light fades to a dim glow. We have pondered the mysteries that remain unsolved, the clustering of distant orbits, the abrupt cliff that marks the belt's edge, the possibility that something massive lurks just beyond our vision. The outer solar system is a place of wonder and enigma. It holds the oldest, most primitive material in our cosmic neighborhood, unchanged since the dawn of the planets. It carries the gravitational fingerprints of events that shaped our solar system billions of years ago. And it may harbor a world, or something stranger, that humanity has never seen. The search continues. Telescopes scan the darkness. Computers analyze endless streams of data. Astronomers debate and calculate and peer through the cosmic murk. Somewhere out there, an answer waits. Perhaps it is closer than we think. The Vera Rubin Observatory will soon open its Eye on the Southern Sky, beginning a decade-long survey that could transform our understanding of the solar system. Within a year or two, we may know whether Planet 9 is real. The longest-standing mystery in planetary science may finally be solved. Or perhaps the mystery will deepen. Perhaps Rubin will find something we did not expect, something that challenges our assumptions and opens new lines of inquiry. Science often works this way. We set out to answer one question and discover that we were asking the wrong question all along. Whatever happens, the exploration of the outer solar system will continue. New Horizons is still operating, cruising through the Kuiper Belt and beyond, sending back data from regions no spacecraft has ever visited. Future missions are being planned, probes that might one day visit the ice giants, Uranus and Neptune, or venture even farther to explore whatever hides in the darkness. These missions will be the work of generations. The outer solar system is so vast that even our fastest spacecraft take decades to traverse it. The people who launch these probes may not live to see them arrive. They invest their labor and resources in a future they will never witness, trusting that their successors will carry on the work. This is the nature of exploration. It is a collective endeavor, spanning centuries and continents, building on the discoveries of those who came before and laying foundations for those who will come after. The astronomers who first proposed the Kuiper Belt did not live to see it confirmed. The scientists who first suggested Planet 9 may not live to see it found. But their work matters. It is part of a story that is larger than any individual, a story that humanity has been telling since we first looked up at the stars and wondered what was out there. Tonight, we have added our own chapter to that story. We have explored the mysteries of the Kuiper Belt and contemplated what might be hiding in its depths. We have learned about the evidence and the debates, the theories and the searches, and we have glimpsed, however dimly, the vastness of what remains unknown. The cosmos is humbling. It reminds us that we are small, that our lives are brief, that the universe was ancient before we existed and will continue long after we are gone. But it is also inspiring. It shows us that the human mind can reach across unimaginable distances, can piece together the history of worlds we will never visit, can ask questions that previous generations could not even formulate. We are part of something grand. The atoms in our bodies were forged in ancient stars. The water in our oceans may have been delivered by comets from the Kuiper Belt itself. The story of the cosmos is our story, written in starlight and gravity and the slow dance of worlds around their suns. As you drift off to sleep tonight, let your imagination wander to those distant realms. Picture the frozen plains of Sedna, where the sun appears as just another bright star in a sky full of stars. Imagine the slow tumble of Kuiper Belt objects, orbiting patiently through the darkness for billions of years. And wonder about what else might be out there, waiting for the day when human eyes finally find it. The search for what hides in the Kuiper Belt is not just about science. It is about our relationship with the universe, our drive to understand, our refusal to accept the limits of the known. It is about reaching outward, always outward, into the mystery that surrounds us. Something massive is hiding at the edge of our solar system, and one day, perhaps soon, we will know what it is. Until then, the darkness keeps its secrets. The stars wheel overhead in their ancient patterns, and somewhere, impossibly far from the warmth of the sun, a world we have never seen continues its long, slow orbit through the void. Sweet dreams. Before we conclude, let us take one more moment to appreciate the sheer scale of what we have been discussing. The human mind struggles with cosmic distances. We use analogies and comparisons, but nothing truly captures the immensity of space. Consider this. If the sun were the size of a basketball, Earth would be a small peppercorn about 30 meters away. Neptune, at the outer edge of the known planets, would be nearly a kilometer distant, and Planet 9, if it exists at its predicted distance, would be about 10 kilometers away, the size of a grain of sand lost in a vast dark warehouse. Now imagine trying to find that grain of sand. You cannot simply walk through the warehouse with a flashlight, because the warehouse is not empty. It is filled with other dust particles, other grains, other debris. You have to distinguish your target from everything else while scanning an enormous volume of space. That is essentially what astronomers are trying to do. They are searching for a small, faint object in an unimaginably vast region of space, surrounded by countless other small, faint objects. The fact that they have made any progress at all is a testament to human ingenuity and perseverance. The distances also affect how we can study these objects. Light from the sun takes about 8 minutes to reach Earth. To reach Planet 9 at its predicted distance would take over 2 days. Any signal we send to a spacecraft in that region would take hours to arrive, and hours more for the response to return. Communication becomes a slow, deliberate process. This is why the exploration of the outer solar system proceeds so gradually. New Horizons, the fastest spacecraft ever launched from Earth, took 9.5 years just to reach Pluto. It has been traveling for nearly 2 decades now and is still in the Kuiper Belt, with decades more of potential operation ahead of it. the outer solar system demands patience, but patience has rewards. New Horizons transformed our understanding of Pluto in a single flyby, revealing a world far more complex and dynamic than anyone expected. Its images of Arakoth provided the first close look at a primitive Kuiper Belt object, a frozen relic unchanged since the birth of the solar system. Every data point it returns adds to our knowledge. Future missions could go even further. Concepts have been proposed for spacecraft that would travel faster, using advanced propulsion systems or gravitational slingshots around the Sun. Some envision probes that could reach the outer solar system in years rather than decades, enabling more ambitious exploration programs. One particularly intriguing concept is the Solar Gravity Lens mission. At a distance of about 550 astronomical units from the Sun, Einstein's general relativity predicts that the Sun's gravity would focus light from distant objects, acting like a natural telescope. A spacecraft positioned at this focal point could image exoplanets with unprecedented resolution, seeing continents and oceans on worlds orbiting other stars. Such a mission would pass through the region where Planet 9 is predicted to orbit. It could search for the planet en route, combining exploration of the outer solar system with groundbreaking science at its destination. The technical challenges are immense, but the scientific returns would be transformative. These possibilities remind us that the outer solar system is not just a curiosity. It is a gateway to the wider cosmos. Understanding our own backyard prepares us for understanding the universe beyond. The connection between the Kuiper Belt and the broader cosmos also manifests in another way. The icy bodies of the outer solar system contain organic molecules, the building blocks of life. When comets venture into the inner solar system and approach the Sun, these molecules are released into space. Some may have fallen to Earth billions of years ago, seeding our planet with the chemical precursors necessary for life to emerge. This is the profound link between the distant ice of the Kuiper Belt and the warmth of life on Earth. We are connected to those frozen worlds in ways we are only beginning to understand. Studying them tells us about our own origins. The search for what hides in the Kuiper Belt fits into this larger picture. Whatever we find, planet or black, hole or something else, will add to our understanding of the solar system's history. It will help us reconstruct the events that shape the worlds we inhabit. And it will remind us that even after centuries of astronomical observation, the universe still holds surprises. As we bring our journey to its end, let us summarize the key points we have explored tonight. The Kuiper Belt is a ring of icy objects extending from Neptune's orbit at 30 astronomical units to at least 50 astronomical units from the Sun, and possibly much farther. It contains hundreds of thousands of bodies and serves as the source of short-period comets. Its structure has been shaped by Neptune's gravitational influence over billions of years. The Kuiper Cliff is an unexplained feature at about 50 astronomical units, where the number of objects drops dramatically. Theories for its origin include the gravitational clearing by a massive planet, the limited extent of the primordial disk, or processes we have not yet identified. The sednoids are extreme trans-Neptunian objects with perihelia far beyond Neptune's reach. Their existence implies some mechanism for lifting their orbits, whether a passing star, a massive planet, or some other influence. The clustering of their orbital orientations suggests ongoing gravitational shepherding. Planet 9 is the leading hypothesis for the unseen perturber. It would be a super-Earth-sized world, perhaps 5 to 7 times Earth's mass, orbiting at hundreds of astronomical units from the Sun. Despite extensive searches, it has not been directly detected. A primordial black hole is an alternative explanation. Such an object, formed in the early universe and captured by the solar system, would produce identical gravitational effects while remaining invisible to telescopes. The upcoming Vera-Rubin Observatory might detect it through flares from disrupted comets. Other possibilities include a concentrated disk of material, modifications to gravity, or the gravitational ghost of a planet ejected long ago. Each hypothesis has strengths and weaknesses, and none can be ruled out based on current evidence. The search continues with increasing urgency and capability. The Vera-Rubin Observatory will provide the most comprehensive survey of the sky ever conducted, potentially resolving the mystery within a few years. Whatever the outcome, we will learn something important about our solar system. The broader significance of this search extends beyond the specific question of Planet 9. Understanding the outer solar system informs models of planet formation applicable throughout the galaxy. Finding a super-Earth in our own backyard would provide a unique opportunity to study a common type of planet in detail. The exploration of the outer solar system exemplifies the human drive to understand our place in the cosmos. That we investigate not because the answers have immediate practical applications, but because the questions themselves matter. Understanding where we come from and what surrounds us is fundamental to who we are. And so our journey concludes. We have traveled from the familiar Earth to the frozen frontier of the Kuiper Belt. We have explored mysteries that have puzzled astronomers for decades and examined the latest evidence bearing on their resolution. We have contemplated planets that might be, black holes that might lurk unseen, and the vast darkness that surrounds our tiny island of light. The universe is strange and wonderful beyond our imagination. Every time we think we understand it, it reveals new depths, new complexities, new questions we did not know to ask. The outer solar system is just one small piece of this infinite puzzle, but it is a piece close enough that we can study it in detail, a piece that might yield its secrets within our lifetimes. Something massive is hiding in the Kuiper Belt. The evidence points to its presence even as its nature remains unknown. Scientists are working to find it, deploying the most powerful instruments ever built to scan the darkness at the edge of our solar system. Perhaps they will succeed. Perhaps the next few years will bring the discovery of a new world, a planet that has orbited the Sun for billions of years without ever being seen by human eyes. The announcement would make headlines around the globe, inspiring a new generation of astronomers and reminding everyone that exploration is not finished, that wonders remain to be found, or perhaps the mystery will persist. Perhaps the explanation lies not in a single massive object, but in something more subtle, more distributed, more strange. Perhaps we will need new theories and new observations before the puzzle pieces fall into place. Either way, the journey continues. The search for what hides in the Kuiper Belt is part of the eternal human quest to understand the cosmos. It will not end with a single discovery or a single generation. It will continue as long as there are questions to ask and minds to ask them. Tonight, as you close your eyes, carry with you a sense of wonder at the vastness that surrounds us. The Kuiper Belt extends silently into the darkness, its frozen inhabitants orbiting patiently through the ages. Somewhere out there, something we have never seen waits to be discovered. And we, the curious inhabitants of a small blue world, are reaching out to find it. The cosmos is vast, the night is long, and the exploration never ends. Rest well and dream of distant worlds. There is one more aspect of this mystery that deserves our attention before we truly conclude. It concerns the nature of scientific discovery itself and what the search for Planet 9 reveals about how we come to know the universe. Science does not proceed in a straight line. It meanders, doubles back, explores dead ends, and occasionally makes sudden leaps forward. The history of astronomy is full of examples. Uranus was discovered by accident, mistaken at first for a comet. Neptune was predicted, mathematically, before it was observed, a triumph of celestial mechanics. Pluto was found through a dedicated search, but turned out to be far smaller than expected, eventually losing its planetary status. Each discovery changed our understanding of the solar system. Each forced revisions to existing theories and opened new lines of inquiry. The search for Planet 9 follows this tradition. It began with observations that did not fit existing models and has developed into a major research program involving astronomers around the world. The process is inherently uncertain. When Badigian and Brown first announced their hypothesis in 2016, they estimated the probability of Planet 9 existing at about 90%. That number reflected their confidence in the statistical analysis, but also their acknowledgement that alternative explanations remain possible. Nearly a decade later, the probability has not changed dramatically. Each new discovery of an extreme trans-Neptunian object has tended to support the clustering hypothesis, increasing confidence slightly. But the failure to directly image Planet 9 has simultaneously decreased confidence, leaving the overall probability roughly where it started. This equilibrium reflects the current state of evidence. The clustering is real and statistically significant. The absence of a direct detection is frustrating but explainable. Neither observation decisively proves or disproves the existence of Planet 9. The mystery remains genuinely open. This uncertainty is uncomfortable for those who want definitive answers. But it is also honest. Scientists do not always know. Sometimes the evidence is ambiguous, the data insufficient, the theories underdetermined. Acknowledging this uncertainty is not a weakness, but a strength. It keeps the door open to new discoveries and prevents premature closure on difficult questions. The search for Planet 9 also illustrates the collaborative nature of modern science. No single person or team can conduct all the necessary observations and analyses. Telescopes around the world contribute data. Theoretical physicists develop models of orbital dynamics. Computer scientists create algorithms to search vast databases. Citizen scientists examine millions of images looking for faint moving objects. This collaboration extends across national boundaries and institutional affiliations. Astronomers at Caltech work alongside researchers in France, Japan, Chile, and dozens of other countries. Data from one survey feeds into analyses conducted by teams on different continents. Discoveries are published openly, allowing the entire community to build on each new finding. Science at this scale is a collective human endeavor. It transcends individual careers and institutional interests. The goal is not personal glory, but shared understanding. When Planet 9 is eventually found or ruled out, the credit will belong to a community of thousands of contributors over many years. The public plays a role too. Citizen science projects like Backyard Worlds have engaged hundreds of thousands of volunteers in the search. Media coverage has brought the mystery to millions who might never read a scientific paper. The fascination with Planet 9 reflects a deep human curiosity about our place in the cosmos. This curiosity is itself worth celebrating. We live in an era when profound questions about the universe can be addressed through systematic investigation. We have instruments capable of detecting faint light from objects billions of miles away. We have theories that predict where to look and what to expect. We have computational resources to process vast amounts of data. These capabilities are the fruit of centuries of scientific and technological development. Each generation has built on the achievements of those before, gradually expanding the boundaries of what can be known. The search for Planet 9 is part of this ongoing story, a chapter that our generation is writing. What will future generations make of our efforts? Perhaps they will look back on this period as the time when Planet 9 was finally discovered, a pivotal moment in the exploration of the solar system. Or perhaps they will see it as a fascinating case study in how science handles uncertainty, a period when the evidence pointed strongly in one direction, but the ultimate conclusion remained elusive. Either way, our efforts matter. The data we collect, the analyses we perform, and the theories we develop will inform future research regardless of what that research ultimately concludes. Science is cumulative. Even ideas that turn out to be wrong contribute to progress by eliminating possibilities and refining methods. This is the spirit in which the search for Planet 9 should be understood. It is not a gamble with winners and losers. It is an investigation, a systematic attempt to understand something puzzling about our solar system. Whatever we find will be valuable because it will add to human knowledge. And that, ultimately, is what this is all about. The search for what hides in the Kuiper Belt is driven by the same impulse that has propelled exploration throughout human history. We want to know what is out there. We want to map the unknown. We want to push back the boundaries of darkness and see what lies beyond. The outer solar system is our current frontier. It is not as accessible as the Moon or Mars, but it is within reach of our telescopes and eventually our spacecraft. The objects that orbit there carry information about the formation of the planets and the early history of our cosmic neighborhood. Among them, something massive appears to be hiding, waiting to be discovered. Tonight we have explored this mystery together. We have learned about the Kuiper Belt and its strange properties. We have considered the evidence for Planet 9 and the alternatives that have been proposed. We have followed the search as it has progressed over the years and anticipated what the future might bring. The mystery remains unsolved, but it will not remain so forever. The tools to resolve it are being deployed. The observations are being made. Somewhere in the data streaming down from telescopes around the world, the answer may already be hiding, waiting for someone to recognize it. One day, perhaps soon, that recognition will come. Someone will spot the faint point of light moving against the stars, or the accretion flare from a passing comet, or some other signature of the massive object lurking at the edge of our solar system. The discovery will be announced, verified, celebrated. And humanity will add another world to its inventory of cosmic neighbors. Until that day we watch and wonder. The darkness of the outer solar system keeps its secrets close, but we are patient, we are curious, and we will not stop searching until we find what hides in the Kuiper Belt. The night is vast, the stars are distant, and somewhere out there, a mystery waits to be solved. Good night. As you drift into sleep, remember that the universe rewards those who look. Every discovery in astronomy began with someone willing to peer into the darkness and wonder what lay beyond. The ancients tracked the wandering stars and gave them names. Galileo pointed his crude telescope at Jupiter and found its moons. Modern astronomers train their instruments on distant galaxies and find evidence of cosmic expansion. And now, we search the outer reaches of our own solar system for something massive that has escaped detection for all of human history. The Kuiper Belt extends far beyond what we can easily see, a frozen wilderness containing secrets about the birth of the planets and the forces that shape them. The evidence tells us something is there. The math points to a perturber, a massive object shepherding distant worlds into aligned orbits. Whether planet or black hole, captured wanderer or primordial, remnant, it waits in the cold and the dark for the moment when human eyes finally find it. That moment may come soon. New telescopes are opening their eyes on the sky. New surveys are probing deeper than ever before. Somewhere in the darkness, an answer awaits. May your dreams take you to distant worlds tonight. May you imagine ice plains lit by a distant sun, orbits measured in millennia, and the slow, patient dance of frozen bodies through the ages. The universe is vast. Rest now and dream of discovery.